help you filter and focus all of this material, and there is. Aside from reactions 14 and 15, and again, I'm about to do this on this paper right here, so don't worry. But I wanted to give you time to pull this up so you can have it as a reference. But reaction 1, 2, 3, 4, 6, 7, 8, 9, and 11. 9, sorry, not 11. All of those reactions share the exact same mechanism. Interesting. Reaction 11, 12, 13. They share the exact same mechanism as well. Interesting. And so if we are going to try and tackle all the reactions that aldehydes and ketones could potentially undergo, well, it appears to me like there are really two things that I need to teach you in order to really summarize everything that you're going to see. And if I can filter and focus this material for you, then I'm really doing my job. And so let's take a look at some of these reactions then. So we finally ported our way into reactions of aldehydes and ketones. And what I'm going to suggest is that aldehydes and ketones, and so I'm going to use this parenthetical H here to denote that there are a number of different reactions that could take place here. So we'll just write reactions. And then they're going to make a bunch of products. So you're really getting your money worth in the last 15 seconds there. Hey, reactions of aldehydes and ketones will undergo reactions and they'll make some products. So nothing fascinating there. But what I want to say is that we can take these and ketones and we can make a bunch of different functional groups. But let's take, we're going to have to then talk about the regiochemistry and the stereochemistry of these reactions. And that's something that's going to be dependent on the subclass of reactions taking place. And what I mean by that is, hey, look at reaction number 1. 2, 3, 4, 6, 7, 8, and 9. All of these share the exact same reaction pathway, mechanism. And each and every single one of these features non-chiral centers. And so in that subgroup of reactions, we won't have to worry about chirality. And you'll notice that the regiochemistry of all of these reactions, 1 through 13, minus 10, and 5, all of these reactions are taking place at the carbonyl carbon. So regiochemistry seems to be the same, taking place on carbonyl carbon, and that's this one right here. It's not a functional group. It's just an arrangement of atoms, but that carbonyl on an aldehyde or ketone is going to be very susceptible for chemistry taking place. And so just be aware that that's likely where we're going to see the region of the molecule change as we progress. And then the stereochemistry, that's going to be dependent. And so again, 1 through 9 here, minus 5. Those all have no stereochemistry involved. And then some of these right in here have some stereochemistry, and we'll make those notes as we generalize these reactions. So if this is the case, then of the reactions, there are really two different types of reactions that we're going to see take place in this in these reactions. Either, and I think we've kind of seen this before. Oh, we did see this before. Hey, I'm just going to pull notes from yesterday. There are some serious perks to doing class online, and these classes online, you can pull from what we've done before. Hey, take a look at... Here's from yesterday, and just epoxide. So hopefully this is too soon to get any PTSD from this. But we looked at epoxides, and we said there are the reactions of, there are really two types. Either you add the nucleophile first, and then you acidify, or you acidify, and then there's some type of nucleophilic attack. And when we looked at the differentiating factors for ethers and epoxides, hey, look, here's 1 and 2. This is a strong nucleophile followed by some type of proton source. And here's all the reactions that occur to epoxides. And hey, look, it's in the presence of acid. No 1s and 2s. Oh, man, I was supposed to hit this one instead. Oh, totally blew it. Okay, let's go back in the Wayback Machine. Here's the H plus set. Here's the nucleophile followed by H plus, 1 and 2, or in the presence of acid. Hey, look, 1 through 9 are all in the presence of acid. And 11, 12, and 13 features nucleophiles first, and then followed by acid. And this one is a little different. We'll explain that. It's actually the same here, but you don't need the 1 and 2 is what I'm saying. But these are all nucleophiles first, followed by acid. So it seems like the considerations that we needed to make to epoxides and there's no and, just the epoxides, that pattern recognition of being able to acknowledge when something is a nucleophile followed by acidification, and those are generally denoted with a 1 and then a 2, versus just everything added all together in acidification and nucleophile attack. If you can identify those two situations, those situations are going to be key when you're looking at epoxides, and those situations are going to be key when you're looking at reactions of aldehydes and ketones as well. If that's the case, then there are two types of reactions. And before I go into that, we spent a lot of time talking about what is the nature of a double bond, and it's always going to behave as a nucleophile. So what is the nature of carbonyl-bearing compounds? And this right here, timestamp this right now. Mark the tape, 10:14. This point right here is the most important part that I can tell you, because the reactions of aldehydes, the reactions of ketones, the reactions of esters, the reactions of anhydrides, the reactions of carboxylic acids, the reactions of amides, the reactions of acid chlorides, all of these compounds are going to behave in the same way with the same mechanism. I will not teach you anything new for the remainder of this unit and half of next unit. You are going to see this motif over and over and over again, because every single time you see a carbonyl-bearing compound, it can be thought of as this extreme in resonance distribution, wherein this species will always behave as an electrophile. And thank God it does. I mean, this type of carbonyl is present in all of your carbohydrates and your sugars. And so this is when I just rode up Elk Knob yesterday. Totally painful ride. Horrible. But when I finally got up that climb, 18 miles to the top of that sucker, I ran out of glycogen. And I needed my body to take the energy gel that I had just inhaled and convert that into sugar. And in order to do so, the chemistry is taking place in my stomach right about this carbon of that carbonyl bearing compound. And so, that becomes really, 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 really important. This motif of treating this carbonyl as an electrophile, get it in your head now. And keep it there. Lock it in there. Draw this picture and put it above your bed so you're looking at it at night, because this is how every single reaction is going to behave as we move forward through the rest of this unit and all of the half of the next unit. I will not teach you anything new. Please, please, please pay close attention to what's happening here. Mainly that this carbon of the carbonyl will always behave as an electrophile. So anything that's negatively charged is going to want to react right here. And you're going to see that over and over and over and over and over again. Knowing that, then there are two different ways by which negative charges can add to this carbon of this carbonyl. And maybe I should, so before I get into this, what I'm just going to write is because this is an extreme, this really exists as a partial positive in real life. So we consider this carbonyl a decent electrophile. Okay? I really put myself, I want these to look so pretty, but this is just going to have to deviate. Or actually, let's do this. Two types of reactions. There is one type of reaction that utilizes the carbonyl as is, okay? And it's going to take advantage of the nucleal or the electrophilicity of this carbonyl, and it's going to take into play the nucleophilicity of any nucleophile that we're adding. And the idea here is that in type 1, the carbonyl is a good enough electrophile and I should have had a different inflection there because that's all I wanted to say. It's a good enough electrophile. That partial positive is strong enough for the reagents that fall into this class of reactions to find it. And so things that follow this type of motif, they add the nucleophile first, and then that is followed, and we saw this with the epoxides, with some type of Bronsted-Lowry proton source to protonate, okay? And so reactions that follow this pathway are all of these reactions that occur here in 11, 12, and 13. And so we are looking at reduction of a ketone or aldehyde. And this reduction pathway uses one, our nucleophile first, which is lithium aluminum hydride, LiAlH4, over a proton source, and water is going to be just fine for this. We could use a slightly acidic condition in our separatory funnel, but certainly lithium aluminum water is fine. Lithium aluminum hydride, we think H-, and so there's our nucleophile. That makes sense. And so this would be reaction number 11. 11, I'll write it over here. Another pathway, Grignard. This utilizes some carbon residue in the presence of magnesium bromide. Follow that up with water, and you're going to get addition to that carbonyl center. And let me just start writing these products out. R. So there's the backbone that was there before. We will get a proton from our proton source, and we will add, and I'm going to draw this line in light blue to denote that the electrons from the nucleophile formed this new nucleophile carbon bond. We end up forming an alcohol. And so now we have to write something about the stereochemistry. Stereochem. Enantiomers produced if chiral. I wonder if this holds true for all of these subclasses of reactions. Let's take a look. If I add my Grignard reactant, we think about this right here as R partial negative, so there's our nucleophile. The product of this reaction will keep our sigma scaffold the exact same. Step 2 will put a proton right here, after step 1 has added our Grignard reactant. We'll put a prime there just to make things a little easier to see. If this was, in fact, a chiral center that was formed, you would anticipate generating enantiomers if this is, in fact, chiral. So it looks like it holds true here. Hey, let's see. Cyano. This also works with cyano, C-Y-A-N-O, hydrin formation. Hydrin being the alcohol, and cyano being the C triple bond end. And it appears like this is done using KCN in the presence of HCN. So not the 1 and 2. They're missing here. But hopefully you see this as our nucleophile. It's our negatively charged species. In this reaction, our sigma scaffold will remain the same. We would end up protonating that alcohol with any HCN in the end, and we end up adding this. And if this carbon is in fact chiral, which it is in this example, enantiomers are produced from this reaction too, as well. So this would be 11, 12, and 13. All of these reactions follow the exact same reaction mechanism that I'm going to take a look at over here. So two types of reactions. We're going to look at the first one here, the mechanism. So no matter what the nucleophile that we are adding is, the pathway by which we proceed in any one of these reactions turns out to be the exact same. Here's another perk of doing this online. I mean, my notes never look this good when I'm in class, and so certainly they look a lot better when I can sit down and actually write instead of trying to write on a chalkboard. So some benefits here. But mechanistically, how can we take a look at the mechanism that's being afforded here? We have, let's just run a simple example here. We'll take this as a ketone, and we will react it with one. I'm just going to write nucleophile. So that could be any of the things in blue. And because we are using these conditions, our nucleophile is going to be pretty strong. So I'm going to write a plus there. And then 2, we're going to write H plus. But we're just going to denote that as HOH like that, so I can keep track of the color. And hopefully in the end, OH, I will mechanistically deduce how this was formed. This carbon is not chiral because it's the same both ways on this side, and so luckily we don't have a chiral center here, but if applicable, we would form an enantiomer. So how would this happen? Well, I have a carbonyl center, and I have a nucleophile. I know that in these subclass of types of reactions that carbonyl-bearing compounds undergo, that this center right here is partially positive. So there's my electrophile. I have nucleophilic attack by that nucleophile at the carbonyl center, and then the weakest bond breaks. Okay? We're going to say this 2-3 more times until I get sick of it. This is going to be the same reaction mechanism you see in dang near every reaction for the next week and a half. The nucleophile will attack the carbon of the carbonyl because that carbon is electrophilic. When that nucleophile attacks, there is a consequence for that. The weakest bond breaks. That is that pi bond, and we end up forming a new nucleophile carbon bond. Again, this is just Lewis acid, Lewis base chemistry. Negative charge must find the positive charge, and when it does that, this carbon must break something in order to accommodate that breakage of the incoming bond, and so it just breaks the weakest bond. This carbon-carbon bond, that's not the weakest bond, so it's not going to break that one. This carbon-carbon bond here, that's not the weakest one. That's a sigma bond, so it's not going to break that one. This carbon-oxygen sigma bond, that's pretty strong. It's not shared equally, but it is stronger than the carbon-oxygen pi bond, and so the weakest bond breaks. And so we have a nucleophile, we have an electrophile. This would just be your classic nucleophilic attack step. Well, then we've already suggested that protonation is the next step of this reaction. I have in solution a incredibly good dark blue Bronsted-Lowry base, and I have this proton on my water molecule that will behave as a Bronsted-Lowry acid. And so what we find here is just taking this negative charge, putting a proton on it to generate our final O. And I'll draw that line in black to truly denote where those are coming from. But that's our H. And then we have this new nucleophile. Could be a hydride anion, H. Could be a carbon chain, Grignard. Could be cyano, C triple bond, N. But regardless, each and every single one of the reactions of aldehydes and ketones in this subgroup where you see 1s and 2s, or this really. You could even write this as 1 and 2, and I would accept it. But these three follow the same pathway, much like these reactants right here in our ethers and epoxides. I'm looking in the wrong spot. Just like in our ethers and epoxides, it's these nucleophile first, followed by acidification type reactions. Hey, same type of motif, just applied to a different functional group. And if you can see that, great. Well, we've got 11, 12, and 13 out of the way of the 15 total reactions. Let's take a look then at reactions of, but now the carbonyl is not a good enough electrophile. And again, this is the type of idea that I keep kind of hinting at. This two molecules on the surface of Mars or in a round bottom flask are similar to you and I trying to play Marco Polo on the surface of Mars or Jupiter rather. It kind of depends upon your flask size. And if you are screaming Marco and I'm screaming Polo, you're the negative charge, I'm the plus charge. And then our intensity of voice is really just based on how strong of a nucleophile or electrophile we are. In the previous example, perhaps you were really loud and I was the carbonyl and I wasn't that loud. But because you were really loud, I could find you. And so that was great. This example's a little different because now the nucleophile is not going to be super strong. So you, as the nucleophile, are going to be just a little bit quieter. But if I could grab a megaphone and turn myself into a really great electrophile and scream Marco Polo, then perhaps you could find me. And that's exactly what's happening here is in the classic organic chemistry world, when we make a new bond, we have to make a new bond from a positively charged species and a negatively charged species. So if you have two species, there's a number of combinations that could happen. You could have a weak negative and a weak positive, and those reactions are going to take a long time to react. You could have a strong positive and a weak negative, or you could have a strong negative and a weak positive. And in either one of those cases, the reaction might go a little bit faster. And then in the best case scenario, you have a full-fledged positive and a full-fledged negative. And those reactions are going to go really, really quick. And there's very few reactions that are like that. And so really what we're toggling here is if you are in a situation where reactions 1 through 9 are, where your nucleophile is weak and your electrophile is weak, we as chemists need to do something to improve the probability of these things finding each other, which is giving me a megaphone, making the electrophile much more positive. And hopefully then the reaction will take place. Yes, these reactions would go without the proton attached, but they would go so slow. We're talking geological time scale. That's not good enough for us. So I'm going to write, can we make the electrophile great again? Make electrophiles great again. Miga, how do we make electrophiles great again? Well, that's really quite simple. We have a electrophile right here that is a partial positive at all times. And if we were to just merely impart a proton onto this molecule or this functional group, the oxygen atom would get that proton by taking these lone pair of electrons and picking up that proton. Correspondingly then, this oxygen would be plus charge. But that oxygen, it's electronegative and does not like to exist like that. And so the most predominant species here is actually this one. Once we've protonated, we effectively turn this carbon into a Miga. We've turned this thing into a great electrophile. And that really becomes advantageous to us because when we look at the reactions that undergo this type of mechanism and fall into the same type of category, we're looking at reactions that involve the addition of water or some type of proton source. So let me write H2O plus here. And then our nucleophile is only partial negative. And so these are the types of reactions where all of these things are combined. And one way to think about a weak nucleophile is that same nucleophile with the hydrogen attached to it. And that's going to turn down its nucleophilicity. The example of that being, here's OH, which is a decent nucleophile. I guess I don't need that line there. I just need to say that is a decent nucleophile. We've seen it react. V, O minus. So this is a strong nucleophile. This would be our weak nucleophile. What's the difference? Well, that oxygen has adopted a proton, and now it doesn't have that full-fledged negative, so it's a weaker nucleophile. These weaker nucleophiles typically show up above the arrow in the presence of acid. Here's the nucleophile, not OH minus, but H2O. Here's the nucleophile, not RO minus, but ROH. Here's the nucleophile, SH, not S minus. Here's the nucleophile, RNH2, not RNH minus. And so all of these species that fall under the category of 1 through 11, sans 10 and 5, all of those reactions right in here feature just weaker nucleophiles, but they are still susceptible to attack an electrophilic center. And it becomes very likely that they'll attack this electrophilic center if we can turn that electrophilic center into a very great electrophilic center, make that electrophilic center great again, and we can do that by adding acid in the beginning. And so before we get into the mechanism then, let's take a look at the reactions that follow this pathway. Hydrate formation. And this would be the addition of water I'm just going to do one thing here. I'm going to take this teal pen. I'm just going to write O right here in teal because I want to show you something. H3O plus. So these are the conditions right here. And it looks to me like in the end, you would end up producing. And this is why I wanted to be really key here. O. It wasn't the oxygen of the carbonyl that's still there. Interesting. And then I certainly would expect to see from my proton source, OH. Interesting. We'll just write plus H2O. That oxygen completely leaves the molecule. I'll come back to that. Hydrate formation. So that was letter number 1. Number 2. Acetal formation. R. I'm just going to write this oxygen in teal. OH in the presence of H3O plus. Number 2. Letter number 2. That ends up producing R. H. Perhaps it becomes a little bit more apparent that the water that's produced here was the oxygen that left. I'm going to make a point of this because I really screwed this up when I took this class, and I really want to drive this home so you don't make the same mistakes as I do. But hey, check that out. Both 2 molecules here have added here. 2 molecules of water have added here. So we can form acetals using this reaction mechanism. Cyclic acetal formation. So this would be letter number 3. That involves the addition of 2 alcohol molecules that just so happen to be covalently linked by an ethene type carbon-carbon linkage. The oxygen of that carbonyl, that eventually leaves. Curious. What else could we use? Cyclic thiol acetal. Sure looks like this is just the addition of SH that is combined in the presence of acid. And if you saw it for oxygen, it's likely going to be true for sulfur, that we make a cyclic thiol acetal. This is an acetal. 2 alcohols bonded to the same carbon is called an acetal. And so we have an acetal, a cyclic acetal, a cyclic thiol acetal, all formed as a result. Huh. Pretty wild. Let's see. All the rest of these reactions with amines. And we won't get into this today. This will be the beginning of our lecture tomorrow. But this would be reaction 6, 7, 8, and 9. 6 through 9. Reactions with amines. And it appears to me that any sort of amine, RNH2, in the presence of acid can be used to effectively add 2 accounts of nitrogen, but something happens here where that nitrogen, before it can add a second addition of that nitrogen, it rearranges, kind of like our acetal type stuff, to form this double bonded nitrogen instead. And it kind of does it twice, twice to form a double bond. And we'll talk about the chemistry that's in here as well. But you also form water where this oxygen was the one that was bonded to the carbonyl to begin with. And so, yes, there are a litany of reactions in this chapter, as evidenced by this bottom half of this pinwheel here. But when we start to look at these different types of reactions, I want to suggest that they all follow the exact same reaction mechanisms. And so if that's the case, then let's take a look at the reaction mechanism that governs reactions 1 through 4 here. So that opens up to the amine stuff that we can take a look at tomorrow. When we say, and again, that'll be a similar mechanism here, the acid catalyzed mechanism then, let's take a look. And so an example of this, we'll take this cyclohexanone, and we will react it with any sort of weak nucleophile, nucleo, and I'm just going to put an H here because all of those nucleophiles has a proton on it. It could be ROH, it could be HOH, it could be HSH, it could be RSH, it could be NH2 and HH. So just be aware that that's possible. And then you would also have your OH2 with this additional proton that's available. So that's in the presence of the H3O plus that you see, or it's written as H in brackets. All right, and from this we would anticipate driving off that O, and in doing so we would end up making water to drive that off. So here's that same carbonyl oxygen, and we have now done something like this. And these hydrogens could in fact be light blue as well. And so I'll just write them there to try and illustrate, and I'll come back and prove that to you in just a sec. They don't have to be. Protons are fairly promiscuous, and so they can exist in a number of different types of environments, but just know they could possibly be that. And so let's take a look then at mechanistically how we would run this reaction, owning that we have a partial negative here and only a partial positive. Could we first impact the chemistry that occurs right here at that carbonyl first? And
why do we go from a cyclohexane to
it's just a mistake. And so let's start off. Our carbonyl here interacting with H2O plus with that proton. First step of this reaction, and this is something we noted at the very beginning, we don't have a good enough electrophile, we don't have a good enough nucleophile, and so as a result, we have to turn this electrophile into something much better, and we will by taking and removing the proton and subsequently making water as a result. And this would be just a Bronsted-Lowry acid-base reaction. We have a Bronsted-Lowry acid here. We have something that will behave as a Bronsted-Lowry base here. And so this equilibrium reaction would impart some type of proton on this oxygen, now making this a full-fledged positive charge. Well, that becomes useful then, because this structure then is in resonance, of which the major resonance contributor will place the positive charge on the more electropositive atom. And so we end up with this carbocation as our predominant species, which is fantastic, because we now have the susceptibility, it is now susceptible rather, to attack by that nucleophile here. Nucleophilic attack should give rise to the addition of our nucleophile to that carbon. But keep in mind, this nucleophile now has a proton on it, and so we're going to have to do something about that. But certainly, that is how that new nucleophile carbon bond is in fact formed. Now, the next step here, in order to drive the reaction forward, involves the proton exchange that I'm denoting with an equilibrium arrow that above it says minus H and below it it says plus H with the arrow going backwards. And what I'm denoting when I do that is simply to say that this whole black to here. What I'm suggesting here is that a proton has migrated from this nucleophile atom, maybe it's an oxygen, maybe it's a sulfur, maybe it's a nitrogen, and has now shown up on this oxygen over here. We could draw a mechanistic arrow for that. And this represents one way by which this reaction could proceed. You could have water one way. Another way would be to have, and I don't want to get too bogged down, but you could have water remove this proton, and then water put the proton over here. You could have, even on the flask of glass where the silicate oxygen bonds are, you could have the glass pick up a proton and donate a proton. When you deal with Bronsted-Lowry acids and bases in the presence of a number of different things with lone pairs, the way by which that reaction donates a proton and accepts a proton could go through a number of different routes. And mechanistically, I can draw one way in orange, but I will not necessarily guarantee that that's the pathway by which this always proceeds. And so that's why I've gone ahead and written minus H plus H there to just kind of invite the ambiguity that is the pathway by which that proton could find its way off the nucleophile and onto that oxygen atom. Now, when we do, all of a sudden, this species, which was a good leaving group, you've got a nucleophile attached to a hydrogen with the plus charge, that could fall off. Just think about your substitution reactions. This is a good leaving group, but when I remove the proton, this becomes, and you won't see this in a textbook, but this becomes a very good staying on group, and this becomes a very good leaving group. Well, interesting. If that's the case, I've got a good leaving group in the presence of another decent nucleophile substitution reaction, SN2. All of a sudden, we have imparted a second nucleophile that still has this proton on it, but we have now jettisoned our, and I'm going to try and keep all the colors the same here. We have now jettisoned our water molecule. Well, that's pretty wild. We just have this species here, this nucleophile, the second equivalent addition of nucleophile with that proton. Removal with the water that was formed because we're under acidic conditions. All of a sudden, we have a Bronsted-Lowry acid-base reaction where we have now imparted two equivalents of nucleophile, and we now have regenerated our catalyst as a result. And so I guess if I were to complete this up here, I'd put a plus charge there with the pink H right here. And so when we look at the reactions that occur when we add our nucleophile in the presence of acid, it looks like we add that nucleophile twice. And so the most important part that I want to impart on us before we finish up today is that when you look at something like this, and reacting that with water in the presence of H3O plus, in the end of this reaction, we would expect to make a dialcohol, and we would expect to make a hydrate. But I want you to understand that during this process, the oxygens that are attached are not the oxygens that were there before. And that's the most important part that I can possibly share with you, is that this oxygen right here is now the oxygen of your water molecule, or regenerated water molecule with the protons on it. And so, or the acid rather. And why I want to make this important distinction is because I made a fundamental mistake, which is that if I were to take this reactant and react it in the presence of ROH in H3O plus, what I want to say is that the product that is formed is not this product. So we're preserving the oxygen here, and we're putting the R group here. This is my mistake, and this is something that I would have messed up over and over and over and over again. And the reason why is because the second addition of this alcohol here would require me to have a leaving group on this carbon chain in order to form a new oxygen-carbon bond. And that's just not going to take place in this reaction condition because we have an electrophilic center right here. We do not have a nucleophilic center. And so this, in order for this to be true, which certainly does look the same as what you see right over here, that oxygen, the difference in which oxygen it is the result of the mechanism and the pathway by which the reaction actually goes. And in order for this to take place, and this is what I thought happened when I took this class, is that once I formed this negative charge, this would react somehow with this nucleophile H. But this is a nucleophile and this is a nucleophile, and those two things will not react together. The mechanism to generate this compound does not go through this oxygen right here behaving as a nucleophile. It goes through this carbon always behaving as an electrophile and substituting out, just like we saw the loss of water here, substituting out for that loss of water. I've had already 3 fantastic questions come out over email. I'm going to make some videos for those as soon as we're done here and start posting those. Keep sending in questions. I'll keep making videos. It is Tuesday, July 21st, and we are done with class today. I will see you back here in the morning tomorrow. Have a fantastic Tuesday.